Okay, everyone, welcome. So this is week 4. So we are going to go through week 3's exercises. So today's agenda is very light. So I'm going to go through some interesting questions in this notebook. So by interesting, I mean maybe relevant for the exams. Most of the questions are pretty old. So I'm gonna also add some bonus questions that might appear in the exam. And also, the last part will be answering your questions about HDFS or the lectures or the quizzes. So let's get started. So this week we've learned, or last week you guys have learned HDFS, and later you're going to also learn MapReduce and HBase, which are the technologies based on also HDFS. First let's go through the first set of questions. These are pretty standard ones. Like the namespace, I think for namespace you can just think of it as essentially the file hierarchy, right? So HDFS has a hierarchical namespace. For the second question regarding the blocks, remember that, so the block files, the size of the block can be customized. Let's see, clients want to send data to it. Yeah, I think let's, do you have any questions for like the first set of exercises? If not, we can just move on to the bonus ones. No specific questions? Okay, then let's go through some extra ones that I added, and I might also add to the exam as well. So the first one would be, remember that the file size can be customized, but the block size can't, right? The replica counts can be customized for per file basis, but not per block. So you can say for this file, it's very important. I want it to be replicated for like 5 times. Others are not so important. Maybe replicate that one for 2 times. For storing a file, for example, 170 megabytes of file, would it eventually require like 2 blocks of 128 megabytes of blocks or not?
No, because you would use one full block.
Yeah.
And, fill the rest in one block, but you wouldn't make it 128 megabytes.
Exactly, yeah. That's true. So remember that, so I've also added some external extra explanation. So basically, always remember that HDFS is parsimonious about the space it has. So if it only requires, say, half of the block, it only uses half of the space instead of the full block. Yes, so the next question. Individual data nodes are not fault tolerant, but the whole system is fault tolerant. Is that true or false?
True. Data nodes can fail.
Exactly, yeah. So remember that, so for HDFS, individual data nodes are not fault tolerant because they're not using something like RAID. Maybe the lecturer also mentioned in the class. So if data node failed, it will fail eventually. But the whole system is designed in a way that is fault tolerant because you have a centralized state, which is the name node, as I mentioned before, and it keeps all the states and can recover any kind of failure. Next question. Name node does not store any data blocks. True or false? Yes. So a name node only stores metadata. Okay. It directly communicates with the users, but it doesn't store itself any data blocks. Another question, name node alone is sufficient to answer to user requests already without needing any information from the data nodes. Is that correct? Is it?
It's a bit vague, right? What does it mean to service a client?
Yeah, for example, a client wants to know if this file exists in the cluster, if the client wants to write a file.
I guess if you want to know if it exists, the name node can help you with that, but to read or write the file, you would have to access the data nodes.
Right. So the actual data operation, so the I/O operation, would have to go through the data nodes. But yeah, I think this was an ambiguous question from last year. But eventually, I think the key idea is that, yeah, so the name node contains all the metadata, the hierarchy, a namespace of the file system. So it can answer theoretically any queries from the user. Yeah. So, but indeed, for real data transfer and writing and reading, we still need the data nodes to participate in this process. Next question. So, name node was a single point of failure of the first version of HDFS. Yes, right? Because previously we only had one name node, and if it fails, we're toast. Next, so the client computes the checksum of each block of the file and stores these checksum in a separate hidden file in the same namespace as the file is. True or false? Any takers? So the checksum is to guarantee the integrity of the data. So this is true. So yeah, in short, basically for every single block, you're right. What the client would do is that first, for example, I want to write a data block. What I do is that I compute the checksum first, and then I send my checksum and the data block together to the data node. And the data node will store that block in the files, in the file system, local file system, and also store the checksum somewhere else, but also in the same hierarchy. And when you request the same block, what data node would do is that it sends the data blocks together with the checksum. So once the client receives this data, it will recompute the checksum and compares it with the original checksum to ensure that the data was not corrupted. So although you like back and forth, lots of computation, you might think, well, this is inefficient. In fact, most of the Intel processors and the chips have already supported this kind of operation in hardware because it's very frequent. Next, so HDFS provides only limited random access capabilities because user can still, access a contiguous subset of the bytes of a chunk of data. Is that true or false? So there are two parts. One part is true, one part is false. to simplify, divide and conquer. Yes, so there are two parts, right? Yeah. Answer?
I guess the first part is true and the last part is false.
The first part, you mean a limited random access?
Yes.
And second part, you mean the contiguous part, like access. Actually, the opposite. Sorry. But yeah, actually, I think this was quite a difficult one, so we didn't really put this in the exam. Essentially, so the first part is false, the second part is true. So you can access a contiguous sequence of bytes in a block, but you can't. But this is not a random access, right? The definition of random access, like DRAM, is what? Is to access every single location in constant time, right? When you scan a thing, it's linear, so it's never constant in that case. So this is not random access. It's still a slow operation. Yeah. Yeah. And yeah, I've added some more explanation here. You can take a look at it later. And also, yeah, reading a row is much faster in DRAM. Any questions at this point?
But didn't you say that under everything is like a normal file system? So
True.
technically it's DRAM, it's a random access.
Yeah, so if the file is cached in memory, then yeah, I think technically you can say it's random access, but typically files are on disk. So if it's on disk, then you need to move the mechanical heads and do the sequential scan of the sectors. So yeah. Why reading a row is faster in DRAM? That's another it's off-topic stuff. Systems architecture. Yeah, because like the specific architecture of DRAM, right? So you pre-charge the row, you feed in the row address, you latch the row data from the cells to the sense amplifier, and you can read the whole row out. If you were to read a column, you need to activate multiple rows and to do this sequentially. Question? Yeah.
But in HDFS, reading any random or any address is in constant time. The constant time is just that you have to download the block in which the location is. So it's still random access, but it's slower according to your definition.
Right. So by random accessing, you mean random accessing a whole block, right?
No, any byte. It's just slow because you get the whole block.
Right. Yes. So yeah, once you get the whole block, you can yeah kind of scan to get any bytes. Yeah.
But isn't it linear then? Like if you want to read the last
Yeah.
byte of block.
Yeah, then that would be linear. Because afterwards you've got, as you said, it would be a file, and you need to still scan a file. Do a read. Once you do a read, for example, in C, you need to move the cursor. Still. Not convincing. Yeah, we can discuss this offline as well. Yeah, but yeah, it's a tricky one. Yeah. Next one. So when writing a file, name node will send the client all the locations of the corresponding data nodes sorted by their distance to the client in ascending order. Ascending in terms of distance. It's a sure. It's a pretty long statement. It's hard to make up something that long, but yeah, this is true. So whenever you write, you want to read or write, in this case, write a file, name node will send a list of locations of that of the replicas of that block, and then you pick the data node at top of the list. Next up, data nodes and name node are typically physical machines running in a data centers. In a data center, sorry. Yeah.
They are processes. on a
Yes.
physical machine.
Right.
So like one data node and one name node doesn't necessarily correspond to individual machines because they are processes and thereby can be on the same machine.
That's true. Yes. Yes. So essentially, so whenever we say, well, it's a node, maybe we are addressing a virtual machine or something, but there are processes actually. So there are processes, daemon processes running in background to do these operations. So they can do multi-threading, forks, stuff like that. So essentially, yeah, they are just processes. Yeah. That's why some students were asking why you have the kind of clients co-located with one of the data nodes. That is because on the physical machine, client was running some processes together with one of the processes being the data node. Okay, that's why, yeah, you have the co-location happening. And once later we'll see the communication. In this case, if the client process and the data node process are co-located on a single machine, then the communication between them would be IPC, right? Inter-process communication. This is very efficient. Yeah, sorry. Question?
So that means that any data node can run on any machine. Like I can become a data node on my computer. Or
Exactly. And you will be becoming a data node soon in later exercise. Yeah, sorry.
Can you have multiple data nodes on one machine?
Yes, you can. In a virtualized environment, you can have multiple isolated processes, each of which will have a single hierarchy, a file hierarchy, because you are containerized in that case.
But they, on a physical level, they would access the same disk, wouldn't they?
You mean on the yeah, that's true. Yeah. If they were located on the same node, then they will be accessing the same set of resources eventually.
But is that efficient?
Well, nowadays we have multiple cores, so that's why you have 200, 300 processes running on your computer. It's still fine. Yeah, sorry, one question. Yeah.
Is it common in HDFS cluster that there will be multiple data node processes on the same machine? Because I feel like that would kind of circumvent the ideas of having multiple data nodes. Because if then the machine fails, then everything on both of the data nodes will be gone.
True. Yeah, you're right. So that's uncommon indeed. Yeah, that obeys the original design. Yeah. Question. Yeah. Thanks. Thanks for the questions. Next question is HDFS CAP compliant? Yes? No? No. It's not, well, it's consistent, it's available, but it's not partition tolerant, because once you cut off part of the network, the data node is done. So you need to, yeah, bring up another data node and replicate stuff again. Yeah. Next one. So when reading and writing files, data blocks never go through. Okay, we've talked about that, and transferred only among clients and data nodes. I think this one is obvious. Clients can customize the replica count for each data block for a file, given their importance. No. Because, yeah, you can customize the replica counts for each file, but not per data blocks. That would be that would be too fine-grained. And edit log contains only the operations after when the namespace file, so the file system image, was created. True. No? Yes. So basically, upon a restart, the name node will check if is there any checkpoints created. If there is a file system image, it will first load the file image to create the namespace, and then replay the edit log operations to get itself up to speed. Second to the last one, observer nodes can sometimes be leveraged to increase the file writing throughput. I guess you guys know what observer node is.
I'm not entirely sure, but I think
Yeah.
in case that you would use the observer name nodes, you would only use them for read access, not write access.
Exactly. Genau. So yeah, so the observer node is responsible for standing there and staring at name node, doing nothing. But sometimes it can be leveraged to increase the reading throughput. So it's basically a hot standby. By hot, meaning that it's always on, and whenever name node is done, it can jump in and to replace the name node very efficiently. And this is a common tactic in most of the companies nowadays. Yeah. Last one, sending and receiving the heartbeats is synchronous. No, it's not critical. Once, as long as it's not critical, both sides don't need to wait for the operation to finish. So it's asynchronous. So the heartbeats is sent periodically, and yeah. Question?
I just don't understand how it can increase the throughput of reading files, because isn't it the data nodes that will read the files? Or?
Right. That's a good point. So essentially, I think, so essentially, I think it only helps if you are opening parallel connections. Yeah, so maybe you are reading different parts of the file at the same time, but you are right. So the name node itself is not responsible for transferring the data per se, but it's responsible for giving the metadata and orchestrating the pipeline and checking the minimum replica count, stuff like that. Yeah.
So that means that if there are too many connections to the principal name node, then it will delegate it to the observer name node?
Yeah, exactly. Exactly, yeah. Good question. All right, so if there is no more question, then we can move on. So 1.2, I think, is interesting. I have listed the solution, the original solution here. So if a typical file system block is basically 4 KB, but for HDFS, it's typically larger because it serves a different purpose. For example, I think the answer is pretty good. So first, it minimizes the cost of seek, because typically in a hard disk, you have the mechanical heads, and moving heads around is basically typically more expensive than just reading a sector. So if you have a larger amount of data, once you move your head to the position, you can read a large amount of data. This, amortizes the cost of moving the heads. And also, it reduces the number of connections you need to make, and sometimes you can have a persistent connection for multiple operations. Questions? Nope. Too easy for you guys. Okay. Okay, 1.3. I don't fully agree, but it's linear. I think it makes a point that HDFS is designed for scaling out, not scaling up. And typically for a scaling out system, you will have a scale out system, you will have linear cost. But I mean, nothing would be free. So it's still like super linear, I have to say, in a real system. Single point of failure, 1.4 we've discussed in previous questions. So you can check out the user guide. There are also all kinds of nodes. I think in previous years there were a thing like checkpoint nodes, backup node, but I think this year it's not very likely to appear. So you can have a look, but yeah, just FYI. Yeah, scalability, durability, performance on HDFS, they are pretty straightforward. I've checked the solutions, they're pretty good. Have a look at it. If there are no more questions, we can quickly move on to the second part. Nope. So file I/O, replication policies. What are the replication policies? What are the steps? If you can remember it. 2 scenarios, right? One is the client being in the cluster. One is the client being outside of the cluster, right? So if the client is inside of the cluster, then where does the first replica go? Exactly. Yes. So to minimize the communication overhead. So often the case we'll see later, the first block, the replication block, is the bottleneck, is synchronous. So the whole cluster need to wait for at least one block to be in a place somewhere in the cluster before moving on to the next operation. So that's why, yeah, being on the same node is rack, would be more efficient. And then we store in a second node and third and so on. Yeah.
I was wondering, like,
yeah.
if you are writing multiple blocks, will all the blocks be stored on the same machine as the, yeah, like if the client data node is on the same machine, will all the blocks be stored on that node and replicated on others?
That's a good one. I guess so. Yeah.
Like the definition of big data is data that can't fit on a single machine. So isn't that a scenario where you can't fit any more blocks in that machine?
That could be possible. So the question is, what if in a case where we have too many blocks collocated on the machine where the client resides, then yeah, if the disk space runs out, what would happen? In that case, then the node will always check the disk space before sending the block. And I think on the slides there are something called if possible, right? So if not possible, then that block will be sent somewhere else. Yeah.
Is it any like pre-fetching strategies? Like if you read block 1, block 2, and block 3 is not on the same disk, then you kind of expect that block to be read, and therefore like you pre-fetch it into that machine from another cluster or rack.
Yeah, that's a good point. Yes. Prefetching is definitely done in HDFS. So when you do like the scanning, the next block will be the next target. Then yeah, this will be fetched ahead of time. Yeah, really good point. Yeah. Oops, sorry about that. Yes, and reading and writing files. So I think the steps are pretty obvious. There are only a couple of things I have added some comments that I like to draw your attention to. So when writing a file, so these are the steps. pretty complicated. So first, the client sends a request to the name node saying that I want to create this file, because the name node first, what I need to do is to register in the hierarchy, right? To create that file in the file namespace. And then the client asks the name node to host the next block of that file. And the name node will, yeah, as we said, reply with a list of locations sorted by distance. The client, I think the fourth step is not very clear, so that's why I added some comments. The client writes ith block to data nodes in a pipeline fashion. So basically, the client connects to the first data node on the list. If it's available, the client's job is done. The data node will orchestrate the writing pipeline and for writing the files. And the fifth step would be, and it's also a bit ambiguous. So here it says that writing pipeline acknowledges the writing of the file. Once all of them replied, the first contacted replies with an acknowledgement to the client. So basically, by replying, it doesn't mean that this block has been stored somewhere else. So say if you have 3 data nodes and all of them replied, and the first data node the client contacted will send an acknowledgement to the client saying that the operation is done, please move on to the next one. This doesn't mean that all of the operations were successful, because that would be quite time consuming. This basically tells the client that all the data nodes have received the notification that they need to write that block. But they can be failures happening during that operation. And if it's failed, the client will still move on to the next block, because the minimum replica count will be guaranteed only afterwards. The fifth operation, yes, yeah. And the sixth one, the client sends the data node a request to close the file, yeah, once release the lock, and then the data node will check, the name node will check for minimum replica count. Yeah, this is where the name node will make sure that at least one block for every file the client writes, there is at least one copy stored somewhere else in the cluster. And for this, HDFS by default is 1. DynamoDB, which is a new, not very new, but newly published key-value stores from Amazon, and this by default is 2. This number is a bit arbitrary, but typically it's a trade-off between efficiency and redundancy. Questions?
What happens when the minimum replication is not reached? Like, does this kind of pipeline just stay on hold until replication has taken place? Or what happens?
Right. So if the minimum replica count was not successful, this writing operation is not successful as a whole. So the clients need to do it again. But of course, for the blocks that's being written, you don't need to do it again. But for the blocks missing, the client, I'm afraid, you need to send it again because it's missing. No copy was in the cluster. So yeah. Question.
Should it be that the name node checks the data node for replication?
Right. I think in this case, this is a bit a weird wording here, but I think it emphasizes that data node initializes the connection to the name node. So basically, it reports that, hey, name node, I have this many replicas. Name node would collect all the information to see if the replica count achieves or not. So basically, name node would never ever send a request actively to the data node. It will only wait for, I don't know, heartbeats or block reports, and just piggyback the commands, the instructions it will send later from the response.
How does it know when to update the name node? Like, how do you know that you like successfully stored the last block of the file?
Right.
Or do you update for every block?
Right. So if I understood correctly, your question is, how can name node knows that? How can name node know whether this the final block has been complicated? Not complicated. Finished writing. I think so. There is definitely a bit of lagging in between, but typically it's a lagging between 2 heartbeats. So after another heartbeat, the name node, if the operation was complicated, finished, then completed, then the data node would report to the name node. Yeah. So yeah, there might be some asynchronous information, but typically it's up to date. Alrighty. Okay. So reading a file is much more straightforward, right? So you just open a connection to the name node to request a file, connect to the first data node on the list, and then you can go from there. The third question, I think, what was that? Why do you think a client writes data directly to? Okay, yeah. So yeah, you should never have a bottleneck, a centralized bottleneck. A centralized component that handles all the requests, like heavy I/O requests, because that would have become your bottleneck in your system. So yeah, that's the answer to the third question. All right. So for question 2.3, so network topology, I think we've also touched upon this question in previous problems. So I think in this case, you can check the answers from the solution directly, but a tip from my side, so basically you can just remember within a node, the distance is 0 because it's just IPC. Within a rack between nodes, the distance is 2. Within a data center between racks, the distance is 4. Between data centers, the distance is always 6. In the exam, seeing this question, it's gonna be an easy piece for you. Okay. All right. Questions? Nope. Okay. Differences between object storage and block storage. I think some questions might root from this kind of questions. So I've provided a lot more details compared to the solution. Please take a look at it. But basically, it depends on your access pattern, the use of your data, and the size of your data. So whenever you are considering which technology you should use, yeah, always considering from these 3 aspects. Right. By the way, I think I was asked by email where my annotation is. So the annotation is in the repository, go to big data, and there is a directory called annotated solutions. So I will upload all the notebooks I've had to this directory. Yes, moving on to 3.2, I think this is also a straightforward one, right? So for Netflix movies, you would store it in object storage. For large simulation data, petabytes of data from turn, it's better to store in block storage. It can scale to petabytes. Object storage also is better for backups for your phones. Yeah, so basically you need to access to every single image or your files individually instead of reading a whole bunch of files sequentially. No questions? Okay, very efficient. Right, so I think next part, have you guys tried the Hadoop simulator we've provided? Not simulator, but yeah, the Docker Compose local deployment. So you wouldn't need to write queries or any operation in the exam for HDFS. But you need to know the kind of operation they need because they can ask you to choose the response for a command, like what this command does, something like, what the operation would look like, stuff like that. Yeah, but basically it's quite straightforward. I've tried myself, everything works like charm. So first you upload a file. So make sure that the name node is always the hash of your container, right? It's never a name because you need to uniquely identify your container on the file. Let me go to directly. And so that's the first point I'd like to highlight. Second point, I think, and also, so basically you provide your hash, colon, and this, the space after the colon would be the namespace in the container instead of your local file. So basically, Docker copy, this file is your local file system, and what after the column would be the file system inside of the Docker container. So it's an isolated, separate namespace. So make directory, put file, this should be, and one thing I find is a bit weird because all the operations were done on data node, but technically you shouldn't. You should, were on name node, you shouldn't, because most likely you would operate everything on data node. So you can replace this with the hash of your data node container, and this will still work. Yeah. And then you can look at it, the files. So once you've uploaded your file to the Hadoop file system, then you can inspect the actual file. So basically, this is a block, and it's stored as a local file. You can't really inspect the content because it's a bunch of bytes, but basically it's a normal file, just like any other like Docker Compose YAML file, things like that. Right. And yeah, you can change the block size. So that's pretty much it. I think that's all the stuff I'd like to cover in this session. So any questions for what I've said for HDFS CLI interface? Nope. Okay. Then let me see my checklist. Yeah, so this week we don't have a JSONic notebook. So this is the only notebook you should practice with. And other than that, yeah, that's it, guys. We've got 2 hours back, I think, 1 hour back. Okay, thank you. Yeah, I will stick around, and if you have any questions, just come to me.